Lesson 6-1A, Simplifying Radicals. What is an exponent and a radical? An exponent has a base. An exponent has an exponent, or you can also call this a power. And it's defined as some base to the exponent. If we have 2 to the 4th power, what we really have is 2 times 2 times 2 times 2. And if we multiply 2 and 2 together, we get 4. And multiplying 4 and 2, we get 8. And multiplying 8 by 2, we get 16. So 2 to the 4 is the same as 16. Now, the inverse operation, to undo this, we use what's called a radical or a root, right? Here, the index is what we're trying to undo. So if we have an exponent of 4, we would take the 4th root of the base here. In this case, the base is 16, right? So what number can I multiply 4 times itself to get 16? And if you go back to this, that would be 2. How are exponents related to radicals? Well, we have radical form here. We have nth roots of a to the m. It's the same as a to the m over n. And we have a fraction as an exponent. This is called a rational exponent. And these are related because we can convert between the two. So we can go from here to here or vice versa. Yes, you can draw some arrows, right? Conversion between the two, back and forth. Here are some examples. So let's rewrite this into a rational exponent, and let's rewrite this into a radical form. All right, to begin, we have the cubic root of 3, or the cubic root of 5 to the first power, okay? If there's no exponent here, we have an exponent of 1. We take the base, 5, and the exponent here for the power of the base is going to be your numerator. And the 3 here, the index, is going to be your denominator. So this is the same as 5 to the 1 over 3. Now to go backwards, we'll take the radical, and our base is going to be inside. The numerator here becomes the power, and 2 here becomes the index, right? So we can have 2 here, or we don't have to write out the 2 because taking the square root is the lowest we can go. So we can have the square root of 3 to the 7th with the 2 or without the 2. Here are some examples. Go ahead and pause this and try it on your own. So if you revert back to this conversion, we can just place the n's and the m's wherever we need. So the cubic root of 5 to the 8 becomes 5 to the 8 over 3. And 8 to the 2 over 3 as a fraction becomes the cubic root of a squared. An exponent expansion is rewriting the base to the exponent to a multiplication. So 5 to the 3 is equal to 5 times 5 times 5, which is equal to 125. And you can read this as 5 to the 3rd power, 5 to the power of 3, or 5 cubed. All right, another example here, we have 2 to the 4th power is the same as 2 times 2 times 2 times 2. That's equal to 16. And you can say 2 to the 4th power, or 2 to the power of 4, or simply 2 to the 4th. Simplifying radicals. So radicals here, we don't necessarily always have perfect squares here. So like the square root of 24, we can't find two numbers that are not decimals in order to multiply to 24 evenly. So what we end up doing is simplifying by pulling out the squares, the perfect squares from 24. That's one method. And the prime factorization is another method of getting to the same answer. All right, the perfect squares method, right, involves factors and perfect squares. So here's a multiplication table. All right, memorize all of these factors. The perfect squares are the diagonals across the multiplication table. So if we go 1 times 1, that's 1, right? Or 1 squared is 1. 2 times 2 is 4, or 2 squared is 4, and so on. All right, 3 squared is 9, etc. So we can use these perfect squares as long as we can identify these numbers on the right-hand side. We'll be able to simplify the radicals using the perfect squares method. Also, the other factors for other numbers will come in handy, so make sure you really understand and have your multiplication tables memorized. All right, example, we have the square root of 16. All right, the square root of 16 is a perfect square right here. We can rewrite this as 2 squared. So we have like that. And because we're taking the square root of a perfect square, then my answer just becomes that base, okay? 4. The square root of 64 can be rewritten as 8 squared. So taking the square root of 8 squared, your root and your square will cancel out, leaving just the base. Okay, so this is equal to 8. Now, because the square root of 18 is not a perfect square, we can actually use the table here to find all the factors of 18. All right, so 18 is right here. We have factors of 6 and 3. 18 is also located here with factors of 9 and 2. And there's also one more factor of 18. That's 1 times 18. So let's list them out here. Over here on the side, all the possible factors of 18 are 1 times 18, 6 times 3, and 9 times 2. Now, this is going to become really important to list out all the factors because within the factors of 18, we can identify at least one to be a perfect square. All right, out of all these numbers here, we have this 1 is a perfect square, and this 9 is also a perfect square. Okay, so we're gonna rewrite the inside of the 18 as the factors of 18 with the biggest perfect square, okay? Always choose the biggest perfect square. Now, to rewrite the inside, 9 times 2 is the same as 18, so I can do that, 9 times 2, okay? And now I can split this into 2. Using properties of radicals, I can do the square root of 9 times the square root of 2. And now that I know that this is a perfect square, right, the square root of 9 is the same as 3 squared. So I can rewrite that as 3 squared times the square root of 2. And canceling out the root and the square, all I have here left is 3, just my base. And this square root of 2, I cannot simplify it any further. So it'll just stay as the square root of 2. So my answer went from the square root of 18, splitting this and using properties, using the factors and perfect squares, down to 3 times the square root of 2. All right, the square root of 48. So here are the steps. Find all the factors. So 48 has quite a few factors. 48 times 1. We have 24 times 2. We have 16 times 3. 12 times 4. And 8 times 6. I believe that's all of them. Let's see, out of all of these numbers, which are perfect squares, we have 1's a perfect square. We never use 1, okay? We're looking for the biggest perfect square. 16 is a perfect square, and 4 is a perfect square. So out of all of these, the biggest perfect square is 16 times 3. Now that we know that, we can rewrite the inside as 16 times 3. Okay, rewrite the inside with those factors. Step number 4 is to split this into 2 radicals. We have the square root of 16 times the square root of 3. And my last step is to simplify the perfect square. So the square root of 16 becomes 4 and times the square root of 3. So this is my answer, simplified. We start off with a number and we split it down into its lowest prime factors. So 100, we can split that into 2 times 50. So 2 and 50 make the number above. All right, 2 is prime, so we can stop here. But 50, we can still split this up. So what can we make out of 50? 2 times 25, okay? And that's a prime number, so we can stop there. But 25, we can still keep going. What makes up 25? 5 and 5, okay? No matter what number you start off and what number you split this into, we could have gone 10 times 10, okay? And we could have split 10 twice. Right? All numbers, every single number has a unique set of prime numbers that make up that number, okay? And that's actually called the fundamental theorem of arithmetic, where any number can be broken down into its prime factors, okay? And no matter what route you make, all these prime factors are always going to be the same. All right, so an example here, we have 50. Let's write that down. From our last slide, we know that you can break this into 2, 5, and 5. Right? They went with 25 and 2. But let's break this one into 10 and 5. Okay? And if we split it this way, 5 is prime. We can split 10 into 2 and 5. Okay? So these are the same factors that we found for 50 over here. 2 and then 5 and 5. All right, the prime factorization method, we'll do the same thing. We'll rewrite the inside, okay, as the factors, the prime factors of that number. So here we have 5 and 5 and 2. Right, taking the square root of this means that I have a 2 here, okay? You may have a cube or fourth or whatever. The prime factorization method says that whatever number is here, we'll have to pair off however many factors we have inside. So here we have 2 sets of 5, all right? Those numbers we can pull out, okay? Remember, we're making groups of 2. We can pull that out. And normally this would be 25, but because we're pulling all these at the same time, we only have one set of 5, okay? So if we pull up one set, we end up with a 5 on the outside. And what was left on the inside was just the square root of 2. So this would be my final answer. The square root of 72. Let's find the prime factorization of 72. So 72, we can do 36 and 2, or we can do 8 and 9. How about we do 36 and 2? Then we can split this into 6 and 6, okay? And we can split this into 2 and 3, and 2 and 3. 3. Okay, so now let's rewrite the inside with all the prime factors. So we have 2 times 3 times 2 times 3 times 2. All right, we're pairing off because this is the square root. Square means 2. And inside of these, we can pair off one set of 2's and we can pair off one set of 3's, okay? So those 2's will go outside. You can pull those 2 out, all right, as one singular 2. And we can also pull the 3's to the outside as one singular 3. All right, so what happens after we pull each of these individually? We're left with, on the outside, the 2 that we pulled out, and we're going to multiply that by the 3 we pulled out as well. Okay. Now what was left on the inside was just 2, so we'll rewrite this as 2. All right, one operation to go. What we pulled out was 2 and 3, so we'll multiply them together. So we can get our final answer of 6 times the root of 2. All right, that makes sense because from the very beginning, if we were doing the squares factors, 36 is a perfect square, and 2. If we were to take the square root of 36, that would give us 6, leaving just the square root of 2 by itself.